Okay, we're gonna start. So it's Memorial Day, but Miss Watkins and I will be doing some recordings today, and kids are not going to school, and therefore
Make sure you have
you're having a feedback.
reverb.
Is that better?
All right, so we're being recorded at the same time we're doing live streaming on YouTube. Shout out to all our educators and students there. And we are going to talk about science and engineering practices part 2. Last week we did the first 3 science and engineering practices, asking questions and defining problems. We're also constructing explanations and designing solutions. And the third one is analyzing and interpreting data. So we're going to continue on with the last 5 science and engineering practices, and it's a week 8. In fact, it is the final week of assignments for our students, and for you guys, my students, this is it. We're home stretch, so we are going to get going. So final week, once again, and before we start, as always, even in my classroom, I always start with a quote: start strong, stay strong, and finish strong by always remembering why you are doing it in the first place. This is one of the things that I've been using as my focus. Always remember why you're doing things, of whatever it is that you're doing, not just in school, but in real life, outside classroom, outside, anywhere you go. Always remember why you are doing what you are doing. All right, so it's Memorial Day, May 25th. Please remember and honor our fallen, and remember that the great sacrifice that they've done for us to make our country great, and of course deserve the freedom that we are experiencing now. Miss Watkins?
Something I always remember was that people would say, freedom isn't free. And although we experience this freedom costs some men and women not only their time, their talents, but for Memorial Day, we honor those who their lives were the price of our freedom. So we appreciate their sacrifice, and we want to honor that by living lives that are awesome and great and to the fullest, but to remember that it did cost some individuals the ultimate sacrifice of their life that they laid down freely for us to enjoy the freedoms and the liberties that we have today.
Yes, and shout out to my husband. I thank him for his service, for going on a tour in Iraq, and I appreciate all his sacrifice.
Yes, and shout out to my husband also. I appreciate his sacrifice in other ways.
Yes. That being said, we're going to get going with this last lesson. Unfortunately, we are going recorded for this week because we wanted to remember our great men and women who sacrificed their lives for freedom. So,
as I like to say in my classroom, thanks, America.
Yes, thanks, America. All right, so today, no school for Memorial Day, but the work still continues. We're actually gonna power through this week, and this is our schedule for the week. Video, watch the science and engineering practices recorded, which is this one. And we're gonna do science and engineering practice 4 and 5, and then that's gonna be due on Wednesday. And then of course, SEP number 3 is due, which was from last week. And I posted an electric motor project check-in for you guys to answer. Are you gonna do it? Are you gonna just make a model? Are you gonna make it work? That's my question for my check-in. Wednesday is, again, if you want to refer back to this recording, in order for you to do science and engineering practice 6, 7, and 8, please do so. and that is going to be due on Thursday. And then again, I assume that you are continuing on working on your electric motor project. I've been asked by some of their classmates, what if they don't have any materials and all that? Please improvise.
What do you got around you? Use what you have.
Yes, it does. If last resort, I really don't have any materials, my parents didn't want me to go out, or we're having a hard time, please, please use whatever you have at home, because you are either going to build a model that's not working. All you need to do when you present it on Friday is for you to be able to explain the mechanism behind this DIY electric motor. Miss Watkins?
Exactly. And remember, your model, it can be made out of found materials. Or Mrs. White, can they do a really nice drawing of a model also? Can that be a visual representation?
That could be.
Explains the parts and pieces and they diagram it with labels.
Yes.
I know some of you have some really great drawing skills and abilities.
Yeah, drawing skills would be it. Again, improvise, be creative. You're not limited to what I recommend for you to use. It would be great for you guys to try it out, because we didn't have the chance to actually build it in the classroom, and which is why I would encourage you to try it on your own. Even if I'm not there, some of you would really go for it. But if not, show me an improvised version of your electric motor in however way you can. There is always a way if you are starting to think and use your left and right brain together. Yes.
And remember, everything is due this Friday at midnight. Notice I highlighted it for you right here.
Yes.
So make sure you get it in. There are no extensions. We have to get grades in. We want to make sure we give you the full credit that you deserve. So get it in by Friday at midnight.
Yes, and of course, on Friday, I will have you guys do your 8th grade science self-evaluation. This is just for you to recap the whole entire year that we spent together in science.
Wow.
Friday, we've gone a long way. You guys have grown to be the best versions of yourself. So let's finish strong this week.
Celebrate and review it. I love it.
We are very proud of you guys.
Reflection is a great way to demonstrate learning.
So what we've been learning, that is your science and engineering practice. We've knocked down 3 and we'll finish 5 more this week. It's going to be short, sweet, but straight to the point. Well, we're going to get going. We're going to go straight away to science and engineering practice number 4. And just looking back on our previous semester, we actually have practiced developing and using models when we made our planets. No, but there are different multiple representation of models when you develop them, and when we actually use existing models, even if it's just in an illustration or a 3D model, that goes along with this engineering practice. And some words that you guys will encounter when you do your science and engineering practice assignment for this week. We have models. So anything that we construct, that we explain something, is a model. And when we try to look at the model, we evaluate, or we try to determine the quality of the model, how well it works. Some model might be better than others. Some models might be something that needs some tweaking, but that's a part of developing and using models. So if you notice last semester, some of you guys used a balloon to make your planet. It kind of didn't work. Some of you guys were successful in using the balloon to shape your planet. Some are okay with like, okay, I'm just gonna get a styrofoam ball, so that'll be easier. But then again, there are different ways on how you want to represent your project that you did in the past, and you are actually evaluating them. Now, systems, it's another word that is related to this science and engineering practice, because we're trying to see how the interaction work seamlessly together to form a whole structure. An example of that is when we made our model of the phases of the moon, for example. on how it actually replicated the phases of the moon.
That was
Even,
so cool.
yes.
So delicious also.
Yeah, so delicious. Some of you guys ate the whole entire pieces, like 8 pieces of them. Some of them like, oh, I don't want to touch that. It's gross. That's okay. All right. And also simulation. It's an imitation or a mock version of a real world process persisting over time. And that is actually the simulation we did in our virtual labs. Virtual labs on collisions. That is an example of a simulation, which is again a model.
Right.
Ms. Watkins?
Exactly. Yeah. I would just like to remind us that all of these different methods can be expressed in different medium or different media. And that's where our phrase STEAM media comes from.
Yes.
Because you can use different kinds of medium to explain your phenomena, right? And so whether you use clay, whether you use art, whether you use simulations, so digital, whether you use found objects, whatever you choose to use to represent what you're trying to communicate and convey, different mediums count. And I also just wanted to point out our connection to multiple intelligences. Again, one of the reasons why we use different modalities is so that way we can learn it in different ways. Because some people, like we mentioned earlier, might be better at drawing or might have a higher affinity for it or might just enjoy it more. And if that's the method that you enjoy, that's the method that you want to use. And so you want to kind of think about tying it back to our schema, remembering what we did last week or 2 weeks ago, the electromagnetic spectrum, right? So all these are the wavelengths on the electromagnetic spectrum, but you find the one that works for you, right? Visible light and color work for Mrs. Watkins, right? But maybe you're more of a pragmatic, black and white, left, or very linear structured. You like the Excel spreadsheets. Maybe you like sticky notes. Maybe you like butcher paper, long paper that's really big that you can fold out and see. Maybe you like grid paper and you like to see the order that way. So again, find a method that works for you and then use that to explain not only your thinking in science, but in your thinking in any of your classes when you're studying a new concept or trying to figure out something that you don't know.
Multiple ways of representation. That being said, these are examples of the models that we may have encountered in the classroom. And I focused more on the science part of it, although there are different models that you can use in history, in English, in math, and PE even. There are different ways in how you can use and develop models in this space. So molecular model is one. The layers of the earth is another. If you take a look at some simulation that we have done on our virtual labs, that's another example, as well as everybody's favorite, the exploding volcano with a baking soda and a vinegar. That is a popular model. And of course, whenever you guys even play games and simulate, let's say a road, for example, from your computer, or even the games you play, that is another model that you use. Now, let's
just wanted to show you right there.
Say again.
Here's our little goldfish, our class pet, right? Hi, Gerald. He has some water molecules there with him.
Yeah. And so let's take a look at some model. And I chose this model in action, which is the volcano. So what is the phenomenon this girl is modeling?
It looks like she's trying to simulate via a model what a volcanic eruption would look like or how it would impact the little village toy houses all around.
Yes, and of course, there are ways that she has simulated this model to the real thing by having the baking soda and vinegar react. So it will start oozing down from the inside of her volcano model out of the volcano.
I also like how she used different kinds of houses. Maybe the houses are made of different materials. Maybe the materials are impacted differently by the volcano. Maybe there are different distances from the volcano. Maybe the volcano's height compared to the houses. Maybe there's a scale relationship there or not, but there could be.
Yeah, exactly. And remember, going back to our definition of of our model of what it means, it actually help us identify some patterns that we could detect when we use this model to explain a phenomenon. But in what ways is her model not like the real thing? So what do you think is it that kind of
Um,
not like the real thing?
well, in my head, I know that it's lava is really hot.
Yeah.
So I'm thankful
Yeah,
that her
obviously.
explosion doesn't have the exothermic reaction going on with the heat.
Yes. There's no smoke, there's no clouds of gas.
Oh, yeah, pyroclastic flow. One of my favorite
Exactly.
words.
So that is not what it's close to the real thing. So that is how we can use a model. Okay. So that's pretty much what SCP number 4 looks like. And in your activity for this week, we're going to use and also hopefully simulate a developing a model based on the assignments that I'll provide you this week. Now let's go to SCP number 5, engaging in an argument from evidence. And I'm sure some of you loves to argue, but this is a different argument. It has to be always based on evidence. And again, argument, um, it's the act of convincing someone or something by claim, sorry about the typo, by stating a claim and providing evidence. Again, stating a claim and providing evidence. Of course, the first part of your argument is a claim. It is an arguable statement or assertion that something is true. Now, evidence is the second part of your argument. Usually, you state the facts that helps prove a belief or suggestion. And of course, after your peer actually have heard your argument, then your peer may discuss this argument that you made and try to compare and contrast any evidence. Either you try to negotiate on an agreement about that argument, or your peer will completely say, yes, you made a point of that argument because your evidence is quite strong. So that's an argument. And when we engage in an argument, arguments could start with the claim based on opinion. Okay, so an example of an opinion. Here's my example. I think the best way to increase our flight distance is to reduce weight. Okay, so that is an argument. And it start with a claim. Another example, only the best predator use a venom. So that's another example of an argument that is based on opinion. Now, argument includes giving evidence. So if you start to kind of like putting a claim, you have to have evidence. So in this case, going to following the first part of your argument is because when we add weight to the wings before, the distance decreased by 10 feet. So that's the following part of your argument. Now, the examples that I placed at the bottom, these are like chunks and pieces of how it looks like. So another example would be because they weigh 120 grams. I mean, it's not related to what I gave you on the first example, but that's another way of citing an argument that gives evidence. Now let's continue to the third one. Arguments are meant to convince someone or something. So they're trying to convince, not to fool them, okay, but to actually try to lean in and say, okay, you have the evidence now, what else? So for example, you use some words as most effective, most accurate. So note though that opinionated words may be used to make the argument sound more persuasive. Okay, so that's why I included most effective, accurate. Um, there are other examples that you can say it's the precision of this um, device, for example, that those are some arguments that are meant to convince someone or something. And lastly, the fourth part of your argument is arguments are often formed from observable data. Okay, so to continue on, 10-foot is used in this example. This data is observable, measurable, and concrete. So these are observable data that would actually make your argument stronger. And also, you try to back up your evidence with data, that makes your argument a strong type of argument that you present to others. Now let's take
For
a look.
observable,
Yeah,
just to be
correct.
mindful that for observable, you can use any of your 5 senses.
Yeah, exactly. And so let's take a look at the
So you want to be
detail.
aware of that. Yeah.
Yes. And let's take a look at this data. So what's our evidence? So based on your data chart, formulate an evidence statement that supports this claim that Kara's paper airplane design is more efficient than Nick's paper airplane design. So let's take a look at our data. So that's our claim. What do you think is the evidence that supports this claim based on the data that we have? Okay, so think about that for a moment. And then let's try to draw some evidence. Ms. Watkins?
I'm thinking Carla's flight path looks a little more straight than Nick, so maybe it might be equal distance, but Nick looked like he took a little turn. And also, I think Carla might have gone a little bit further because it says her data point goes until 25 feet, when Nick's only barely reaches 20, so not even 20, so maybe about, I don't know, 18-ish.
Right. And remember, we are actually trying to make an argument, but we also use the data that we have in order for us to support the argument we're trying to make and support that claim based on the evidence on the data, which is why this is our evidence. Kara's airplane flew 25 feet, while Nick's paper airplane only flew about 18 feet. So the airplane that traveled longer distance would be considered more efficient. And if you notice at the end of my statement, more efficient, that is actually something that could persuade or convince, okay, the audience that our evidence, our claim is supported by this evidence based on the data that we have on this chart. So that is, of course, using evidence to argue a fact or an observable fact that we see based on our experiment in this example. Now let's move on to
and also consider
number 6. So SEP number 6 is obtaining, evaluating, and communicating information. So if you notice, there's a lot of things going on, but we're going to take a look at that one by one. So when we try to communicate or obtain data and try to evaluate the data or information to be valuable, of course, we have to find source first for obtaining some information. So it could be a person, a place, or a thing from which information is obtained. And of course, that source could be media. The particular method of or means, sorry about the typo, I did this last night, so I'm like kind of tired, but so a particular method or means by which information is shared with others and evaluating. Of course, if we try to find some information, we have to see if it is accurate, credible, and of course, see if there might be some bias in that information published that you were using. You don't want an information that is false, okay? Because when you present it out to others, okay, your information must be reliable for others to use in the future, because potentially, for example, in science fair projects, okay, other students might want to replicate your study or your research, and therefore we have to present and communicate data or experiment or project that is accurate, credible, and they can use in the future.
replicable.
Yes. So where can we find information? So there are a lot of ways we can find information, but these are what I would recommend. Textbook. Of course, textbooks are written by experts and in specific subject. It can be any subjects, not just limited to science, but also other subject area. Another example of where we can find information is online resources like database, online encyclopedia, any resources that has .edu or .gov or .org websites could give us reliable information, and also some primary literature. So what does that mean? These are research papers, articles, and journals. Okay, not just in science. If you're interested with other subject areas, social sciences, that is a good way for we can find some primary literature that actually shows us information on whatever information we're trying to find based on, yeah. So,
and with that too, to be mindful that your sources can also be primary source individual. So maybe you could talk to somebody who's actually been in a volcano. Hello. Or maybe talk to somebody who's been in a natural disaster before, or experienced snow, or seen a phenomena with their own eyes. Maybe they weren't there, but maybe their parents were. And so going to those first person sources, that's why I drew my little person with a talking symbol here. That's another source of information for you to speak and to gather information to increase your knowledge and your understanding of a topic.
Yes, it could be someone who is an expert on the field that you're trying to study. So that is another primary source of information.
Or experience.
Yes. Mm-hmm. So
experts have experience
that we can get out of different sources or media. So reference books. So these are some information that we can look for quick facts, statistics, or data. Those are reference books. Nonfiction books, of course, that's your textbooks. It can provide us information, nonfiction textbooks. Science journals, these articles written by doctors, scholars, and experts, and of course that brings in new research in whatever field they are involved in. Audio and video, we can look at documentaries, History Channel, Discovery Channel, and also other media that provides us visuals and sounds about a phenomenon. Magazines are another way we can find some information. Usually these are current events, whatever field that might be. Magazines are the ones that usually print out and publish information that are current. And lastly, the website or search engines. These are digital collection of any web pages, multimedia, or content that is, of course, dedicated to a particular topic or purpose. So we start searching Google and stuff like that, and we can find vast of information if we use websites.
And again, this is our STEM media concept, right? Our STEAM media, that there are multiple forms of media that you can go to gather the information that you need. And again, also people are a resource too. So all those people in the library there, as they're learning and reading different things, they either have more knowledge than you do at the moment, or maybe they have some first person knowledge or a story or a real world experience that they can share about their interaction with a phenomena that you're trying to gather more information about. So don't be ashamed or afraid to ask people for help or for questions, or to share some of your wonderings with them, because maybe you can explore things together, or maybe you might discover that they might know something that you don't know yet.
So let us take a look at some of these media that you should use or maybe not use to find information. How do you know if the information is credible? So this is an example of an activity. I wish I would have had the time to have you do this interactively, but I just wanted you to do this with me right now. Let's circle or cross out the ones that are not credible, but circle the ones that are. Let's start first with USDA.gov. What do you think is that? Is it credible or not credible?
I'm gonna go with right here, credible.
Let's take a look. It is credible.
Yes.
So life science, I'm sure you're getting the hang of it. Even if it's just the first, it is credible. How about the PBS science documentary? What do you think, Ms. Watkins?
I'm gonna still go with credible, because PBS, the public broadcasting system, seems pretty credible, and a documentary is documenting things that actually happened.
Exactly. That's right. And how about YouTube?
Ooh, I think I might have to make an extra symbol up here.
But you know what? You know,
sometimes
some people would say it's helpful. I can find some tutorials and stuff like that. But then again, we have to see and think about how credible they are, which is why we can't really consider YouTube as a credible source.
That's why I made a squiggly, Mrs. White. So I'm thinking outside of the box for you.
Yeah. How about answers.com is another source that might not be credible, because these are kind of like a crowd sourcing type of website that has
open source database.
Yes, it's open for each and everyone's views and answers, so which is why it's not credible. Same with Google.
And
yes,
exactly. But to give you the point too, even Wikipedia, answers.com, YouTube, those might be good places to start, but each one of those sources also has a reference page. So even if you start at the beginning, you know, gather a little bit of information, go to their sources, go to the source of the source, you know, figure out where they got their information from, and then you go get it directly. So that's the phrase, go to the source.
Yes. How about this National Science Review?
Ooh, I'm going to go with that.
That is actually a credible source. So this is a journal, okay? Wiki Answers. I know this, some of us are pretty like, oh, I'm going to find the answer, type it in Google, and then automatically some of the wiki answers are there. Unfortunately, this is not a credible source. And how about a newspaper article? What do you think, Ms. Watkins?
Ooh, I guess I would go to my maybe.
Maybe.
Because it depends on who's writing the article. It depends on what media outlet is putting it out. They might be slanted or persuaded a certain way.
Yes.
But depending on that. So that's why we go with my maybe column.
Yeah, and we can actually and easily say when in doubt, it might be a credible source, but it might not be. But newspaper articles that might give them their view, like when we go back and give us an argument, they have a claim and they have their evidence, that could be a possible credible source. American Journal of Medicine.
A good first.
It is a good source because
I'm going to go with
yeah, exactly. How about Time Magazine?
If there was a continuum, I'd put it between here, between the yes and the maybe.
Yeah, but it is a credible source. And encyclopedia, obviously, it's at the library.
I'm going to say yes. A hard yes, as we like to say sometimes.
Yes, it is a hard
yes. It's a hard yes.
We've been using that since there's no internet. I've used that without the internet, and it has
my goodness.
A reliable.
I remember books and books of like Encyclopedia Britannica.
Encyclopedia, you know,
volumes.
Yes. Yeah, and every so often, if you buy a volume of encyclopedia at home, you know, you need to update them. I don't know how many years will that fact.
I was just thinking about that, Mrs. White.
Yeah, I was like, okay.
Literally.
Yeah, but
because think about it, you guys.
Yeah.
The internet that you have now, you can update information continuously. But when they printed materials and put them in our volumes of encyclopedias, they could only reprint those every few years, you know, because you print one, everybody buys it, and then you have to buy a new one the next year. Because remember, information gets outdated as soon as it gets printed almost. Yes. Some information. Because remember, some things never change, but some things do. Yep. And so as more information comes out, it has to be adjusted and added to. And that's one of the things, honestly, Mrs. White, I love about science, because it's always changing and growing. And again, some things don't change, but some things do. And so it's nice to have that blend between them, that we can rely on certain truths to be true, but then also we can challenge other assertions by gathering new information and new data as new information comes out.
Exactly. How about an essay written by a friend?
Unless your friend's like a scientist.
Well,
So it
yeah,
depends on the friend.
essay, but yeah, you know what? An essay that might an expert might have written down might not be
See,
until it
so
is published, until it is peer reviewed. That's when an essay could be, of course, a reliable and credible source. Otherwise, it's not a credible source. Obviously, science textbook, it is a reliable source. How about a blog site?
yes.
You know,
Again, depends on who's writing it, but I'm going to go with a general, probably not.
nope, it's not. How about Wikipedia? This is the most popular one that everybody was trying to use whenever they try to write. Even the informal research that I give out to my students, to you guys, I don't know, but it is not.
If you remember, I gave the hint earlier on this one, and I'm going to say no with that. It's a good place to start, Mrs.
Yeah,
White. You know, you can read it, you can get some quick information, and it's like a
exactly.
spark notes.
Yes,
It can give you a
exactly.
quick introduction, but go to the source. Go to Wikipedia sources at the end of their references,
Reference.
and
Yeah.
then go to that source directly.
Yes, they actually direct you to the source in itself, which is good. But
Yes, they do.
Wikipedia is not credible all the way through because they also rely on factual sources, like the actual credible sources as well. Okay, so just to recap, how do you present information? So if we have obtained information, we also want to communicate our findings, especially if we are doing science fair project or research, even presentation in your classroom. Of course, we found resource. We just to recap, we look for source where we can get information from, and of course, if we're presenting to our community, what do you want to communicate to your audience? Who are your audience? And of course, what means of communication? How are you going to communicate that? And how will you make the info easy to understand? Well, that would depend on who your audience is going to be. And of course, are they going to be able to understand your presentation? And of course, be open to
Being mindful of the audience. That's a good point, Mrs. White, because if I'm trying to talk to fifth graders versus a panel of scientists, I'm going to speak very differently. Or even if I'm speaking to someone older than me, someone younger than me, or my peer group. So being mindful of the audience will change your vocabulary. It might change the way you present the information. It might even change the output.
That's true. That is true. And which is why it matters of what mode or way you are going to communicate with this information that you might have. It could be a model. It could be a live experiment. It could be a slide presentation, a brochure, a video, just like what we're doing right now. And of course, it could be a poster. The poster board is actually the most common that we use in science fair projects. So that is our science and engineering practice in terms of obtaining and communicating our information, which will lead
And
us.
potentially we could put an extra one on there that says other.
Yeah, and others.
There's always other options.
Other options. Again, creativity is the key. Now let's go to the next science and engineering practice, which is planning and carrying out investigation. Now, planning and carrying out investigation could be a part of a research that you can communicate based on what information we have obtained. And if we want to test that information, we can plan and carry out investigation. Now, some words that's used in investigation is are these words: variables. During an investigation, some variables can be changed or kept the same. So that's when you have your control and experimental group, for example. You also have trials. Whenever you are trying to conduct an explanation, not an explanation, but investigation or an experiment, it is safe to say that we try to conduct multiple tests to get accurate results. One trial is not enough in order for us to verify the accuracy of the results that we might get based on the test that we're trying to make. And
a helpful rule of thumb with that one is usually a minimum, absolute minimum of 3 to have a statistically significant number. And I mean, think about it also when you're making a number line, right? You don't just start with the number line and you put your number in the middle. You usually want one to the left and one to the right to denote whether it's positive or negative. So if this was 8, then I put a 7 here and I put a 9 here, and then you know which direction things are going. But if I just put an 8 there, I could be going whichever way and you don't know. But by having at least those anchor points on either side, it can help you to do that. 3 minimum, 5, then I would go to 10. But 10 is usually a good base number for number of trials.
Yeah, and of course, when even prior to actually doing an investigation or an experiment, we have to plan first. And there is a series of steps that you have to follow. And the previous science and engineering practice that we learned last week is, of course, starting off with observing a phenomenon. And then we start asking questions. Then we start gathering materials and identify the variables if we are trying to prove something based on what we see, based on the evidence we have. We're trying to hypothesize and say maybe prove a hypothesis to be right or wrong. And then we carry out investigation where we conduct trials, gather data, and draw conclusions. And if there's a need for us to repeat the investigation to verify the accuracy of our results, then that is usually what our scientists use and do in order for their research to be deemed valid. And if you are thinking about in the science community, it has to be evaluated by other experts and scientists before it can actually be deemed to be something that could be a new research that could be added in the future. And of course, even those theories and laws that we have currently, theory of evolution, laws of motion, scientists, physicists, or experts actually evaluate those theories and laws and continuously they've been, but once it becomes a law, you can't really contest that. Theory, though, you can try to prove it wrong, but it takes years and years and years to prove a theory wrong. That's why it becomes a theory, because if you want, there's always a bigger chance for it to be a reliable research or study, just like theory of.
And then, again, things can happen. Things can happen. But off of variable, just really quick, Mrs. White, I wanted to make that connection. That's a math term, right? So be mindful, you guys, that variables remind you of math, like you have your X and your Y while you're trying to find your unknown. So it's very important that variables change over time. So it depends on which variable you want to look at. So those can be very different investigations. Maybe I'm looking at it for this variable, that variable, time, distance, speed, all the different things. You can conduct the same experiment, but looking at different variables will give you different information.
Yeah, exactly. So let's take a look at this example of what investigation do you think is worth conducting based on this image. So let's say, for example, Johnny here noticed that when he took out a penny in his pocket from swimming, he started to notice that there's like drops of water that's pulled into his penny. And what do you think is worth investigating based on this image? So I think when we discussed for 7th graders that we have, Mrs. Watkins, we tried to take a look at the properties of water, right? And it is something that we wanted to find. It could be how many drops can a penny's surface would be able to handle. And of course, if that is something that's forming into your mind in order for you to want to investigate them, then of course you want to think about the next step, which is to what materials do you need? So we already see on our setup that we need water, we need a dropper, and of course we need the penny. And of course we, again, when we try to carry out an investigation, we want to test our investigation more than once in order for us to do to get accurate results. And how will you repeat the investigation?
Statistically significant.
Statistically
significant.
Yeah,
Is it replicable?
yeah, when you move in high school, that is something that you always want to think about. It's not like, okay, I'm going to do an investigation, one done. No, we can still modify and change possible setups, especially after we try it, the first three trials. Some experiments can actually yield a different results when you try to change the setup. So that is always a good way in order for you to make sure that your investigation would be a reliable source of information after you gather your
An
results.
expert tip for us, Dwight, on that one, if you ever are in a science fair as a science fair judge, Greater San Diego Science and Engineering Fair, as a judge, one of the questions we always ask, just to give you that helpful tip from an expert, right, is what would you do next time? Yeah. How would you continue this experiment? Either are you going to continue to do the same thing, and would you like to ask a different question, like Mrs. White said, or are you going to do something totally different, like a different investigation, or take the same topic and explore something different, like a different branch or a different lining of questioning? So thinking about different, or maybe no more experiments. Maybe you're like, I'm done with experiments, right? There's lots of different options, but always to think about what's that next step? What would you do differently next time based off of what you just discovered this time?
Yeah, and let's take a look at some examples here. We are down to one more science and engineering practice, but these are some examples that I want you to think about. We're not going to get to this together, but I want you to think about these setup or investigations. So it always starts with a question. Will the food I eat on the top right side, will the food I eat affect my heart rate? So in order for you to try to see and answer that kind of question, you might want to investigate. Maybe for 1 week, Gary ate a balanced diet, and the following week he ate only fast food, just like the Supersize Me, and try to see.
Like fast, oh.
Yeah, and try to see his heart rate and how food affect his heart rate. And of course, like I said, we always want to plan an investigation that would give us results. Same with the second one. Does the type of sports ball affect how high it will bounce? Now, this is a good example that you can actually carry out investigation on your own. Okay, so investigation, Mia dropped 5 different balls and observed their return bounce height. And then she measures it, different ball, tennis ball, ping pong, dodgeball, you have your volleyball, you have your soccer, basketball. So hopefully you'll get the chance to do that. And lastly, what effect does air exposure have on the rate of molding fruit? So you might have some fruit lying around and nobody's eating it. Then you might want to investigate on placing that fruit inside a Ziploc bag and try to see what results could arrive and could be we could find in this test. Okay, so these are examples of.
I'm already thinking about all of those, Mrs. White. Those are all very good. I think I'm most interested in the number 3 one. And then not only am I thinking about Ziploc bag or not Ziploc bag, I'm also thinking about refrigerator, freezer, outside versus inside.
True.
You know?
Yeah, that's another.
And there's a lot of different variables that you could explore there.
Exactly. Perfect. And lastly, we have SEP number 8. Not everybody loves math, but math is a very integral part of science and computational thinking.
It's a wonderful thing, you guys. Math is a wonderful thing if you've seen School of Rock. And if you haven't, go watch it.
Of course, what ties in with mathematical and computational thinking, you always talk about units. These are quantity as a standard measurement. We learned about Newton force, meters per second for speed. You have grams to measure mass. We measured mass in our weighing scale on our digital scale that we have in school. We also measure gallons for liquids, and of course meters per second squared for acceleration. These are units. And also
and
mathematics.
time.
Yeah, time is another.
Hours, minutes, seconds, milliseconds, weeks, days, months,
units,
years
that you can use that is, of course, tied up to mathematics. Same with operations, plus, minus, divide, multiply. So we add, multiply, subtract,
Yeah.
and divide to solve a problem. And that is always tied up with mathematics and computational thinking, as well as quantitative words that such as quantitative. So we're trying to describe exact amount of something by using numbers. So we use numbers. Okay, numbers will give us exact visual of what we're trying to figure out. And lastly, of course, another word would be computation. When we try to calculate math problems through the use of calculator or computer, we are actually computing. Okay, now let's take a look at this example.
Numbers count.
And
numbers count
is actually used in biology. So this is just one example how we can use math and computational thinking in biology. So let's take a look. How would you describe the rate at which cells divide? So 6th grade, we learned cells. Okay, so if we start off with one cell at stage 1, once it enters stage 2, there are now 2 cells. Ooh. Once we get to step 3, we get 4 cells. So we cells divide and there's 4. Okay, and then by step number 4, we produce cells. So if you could show this trend as a formula equation, how would you write it? And what do you think results into this? So let's take a look at the numbers.
I'm not going to show my answer yet.
From one stage to another. So it actually kind of compounded. So we can see some patterns. And by the time we reach stage number 5, there are now 16 cells, right? So it kind of like doubles. So from 8, it turns into 16. Now, what do you think is the next number, Mrs. Watkins, at stage number 6?
I wrote 32.
Yes, it is 32. Yep. And of course,
for 16 plus 16.
Next stage. So now that we have 32, we are getting a pattern, correct?
Yes, ma'am.
What pattern is happening? What pattern can we observe in this stages when cells divide? So stage 7, let's answer first. In stage 7, how many cells do you think will we have by that stage? And remember,
64.
It is 64. So 32 doubled to 64. And then let's move on to stage 8. What's going to happen is 64 doubled into 128. And then stage 9, 256. And stage 10, 512. So we are actually practicing some computational thinking as soon as we see some patterns in this setup or scenario that we have. And the number of cells that we see here appears to be doubling at every stage. And we saw that pattern early on. Now, this means that not only cells are increasing, but their rate is also increasing. And this is actually related to the patterns that we see in COVID-19, right? And
yeah, that's what I wrote.
Yeah,
2x.
Exactly. So this is called exponential growth. So in math, when you go to your math classes, they call it exponential growth. But I am biased because I'm science, but we make sense of what exponential growth means by looking at some examples that we observe in nature, what we observe in cell division, and that is your math and computational thinking. And where else can we actually use mathematics and computational thinking? We can use it in physics, we can use it in engineering, chemistry, geology, environmental physics, and science, of course. There's environmental physics, and then astronomy, and a whole lot more. So I cited some examples that we have used in class. Physics, 4 is equal to MA. Engineering, you got your gear ratios in car, like the gears, and then balancing equation, geographic map scales, calculating electricity consumption from solar energy. Some of us were like, okay, I want to use solar panels in my house. And of course, when you calculate that, that has to do with environmental science. scale of our planets, you know, when we try to take a look at, okay, how big is Mars, how big is Saturn and stuff like that. Of course, it has to hold true when we try to represent it in their scale sizes, and which is why we are still kind of using math and computational thinking, and when we try to take a look at scaling and sizes as well.
Yeah. And a fun fact for that, I like to say that math and science are BFFs, right? So our STEAM, our science, technology, engineering, and math, they're always interconnected. Also with history, English, literature, everything's always connected. That's why we call it STEAM IO, right? Input and output. Whenever something comes in, we can connect it going back out. But math and science in particular, math, they call it the universal language, even more so than English, right? Even more so than words that we communicate. So we can communicate with numbers to represent quantities to help us explain scenarios and phenomena. So that's why all of it is connected. So even if you are not a big fan of math, you probably use math more than you even realize or recognize yet. So I hope you would come to like it a little bit better, and maybe we can provide those positive experiences with the content for you.
Yes, and lastly, and of course, just to prove that point, is that when Isaac Newton tried to say, okay, an apple fell on my head, and that starts with an idea, and that idea can actually be explained using math, then he proved this point about the laws of motion, of proving that F is equal to ma, and that equation in itself is math, and that math supports his law and explanation in order for us to say, okay, well, what about force? Like if you increase the mass, what happens to the acceleration of your car? And you can prove that and see the numbers that yes, if you increase the mass of an object with an equal amount of force, the acceleration would decrease because I did the math.
Proportionally. Yep.
Exactly. So this week, just to recap, and I'm sure you've seen a lot of information that you will find it useful when you do your science and engineering practice that that I've explained. So please make sure that you go back to this recording in order for you to answer science and engineering practice 4 and 5, which is due on Wednesday. It's already up and posted on Google Classroom. I also have the check-in for your project that's due tomorrow. Not tomorrow. Yeah, tomorrow. That's right, Tuesday. And then science and engineering practices 6, 7, and 8. That'll be posted tomorrow as well, but it's not due until Thursday. Now, the last piece of requirement that you need to turn in would be your electric motor project and your 8th grade science evaluation form, which is due on Friday. No extension, unfortunately, because we are going to finish up our grade and turn in our grade soon. Mrs. Watkins, you have anything more to say? Thank you for joining me today.
Oh man, it's so fun to join you. I am really excited. I'm looking forward to finishing this year strong like we talked about. And if you guys have any questions, please feel free to let us know. We're available via email or on the line, right? With Mrs. Watkins STEM and Mrs. White online.
Exactly.
So ask us questions if you have any.
My homeland, so I will be saying goodbye for now, and please send us and send me a message if you have any questions on the assignments throughout the week, and I'll be there posting and guiding you guys, so hopefully we'll get that done. Thank you so much for listening, and I hope I'll be helpful throughout the week.
You matter.
Yes, you matter. I mean, get a light, which is E = mc². Bye.